Welcome to the Deep Dive, where we get past the headlines. Today, we're diving into something absolutely critical for, well, basically our modern world.
That's right.
Think about the phone you might be holding right now, or maybe an electric car driving by, or just the huge push for a carbon-neutral future. There's one element kind of powering all of that, the unsung hero maybe.
Lithium. Definitely lithium.
Exactly, lithium
Yeah.
is fueling this whole clean energy shift.
But there's a catch, isn't there?
There is, yeah. Big one. Getting enough of it and getting it sustainably, that's the real challenge. Most of it comes from these huge Salt Lake brines, places like South America.
Right. Vast reserves there.
But the lithium itself is actually in really low concentrations. It's like it's swimming in this complex soup with loads of other ions you don't want.
A whole cocktail of things like sodium, potassium, magnesium, calcium.
Right. Trying to pull just the lithium out of that mess.
Uh-huh.
It's like finding a few specific tiny marbles in a giant pool filled with thousands of almost identical ones.
That's a great analogy, actually. It really captures the difficulty.
And the way we've traditionally done it, solar evaporation and precipitation, it sounds almost quaint.
It's pretty low-tech in practice and slow.
And the environmental side? Not great. You're talking hazardous chemicals, huge amounts of waste, these massive ponds taking up land.
And it takes months, even years sometimes. Plus, it completely depends on the weather. Sunny and dry, great. Rainy season, problems.
Yeah, exactly. So it's definitely not the clean, efficient process we need if we're serious about green energy.
Absolutely not. The need for something better is urgent.
So that's our mission today on this deep dive. We're going to unpack some really groundbreaking new research. It offers a potentially much more sustainable and highly selective way to get lithium from these tricky brines.
Sounds fascinating. What's the source?
We're looking at a study called Selective Lithium Extraction from Salt Lake Brine using LATP-incorporated cellulose membranes in electrically driven systems.
Okay, LATP-incorporated cellulose membranes. Lots to unpack there.
Yeah, our goal is to figure out how this membrane works, why it performs so well, apparently, and what it could mean for our energy future. So let's start basic. Why lithium? Why is this element so essential?
Well, it really comes down to its unique properties for energy storage. Rechargeable batteries, that's the core of it.
Right. Phones, laptops.
Exactly, all the portable electronics we rely on. But now, the massive one is electric vehicles.
Huge demand there.
Huge. And even bigger picture, large-scale grid storage.
Right.
Smoothing out renewables like solar and wind. Lithium-ion is currently the leading tech for that.
So it's really the foundation for moving away from fossil fuels.
It absolutely is. But as you said, the challenge isn't necessarily a lack of lithium globally. It's quite abundant, actually.
Well, that's interesting. Yeah.
Yeah, but getting it out economically and crucially sustainably, that's the bottleneck. Those salt brines are a major source, but they are incredibly complex mixtures.
Back to the marbles in the swimming pool.
Precisely. You need that high precision to separate lithium from all those other ions.
Okay, so those traditional methods, solar evaporation, clearly have major downsides. Slow, wasteful, weather-dependent, chemical-intensive.
All of the above.
Which makes the search for better alternatives incredibly urgent, doesn't it? We need high selectivity, eco-friendliness, energy efficiency. It's not just a wish list anymore.
It's essential. Which leads us to think about what other approaches have been tried before this new membrane came along.
Right. What were the stepping stones?
Well, science has definitely been moving towards membrane processes. They offer a lot of advantages, generally more eco-friendly, potentially more energy efficient, and easier to scale up.
Like super advanced filters, basically.
Kind of, yeah, at a molecular level.
And some previous membrane types, like nanofiltration or NF, they showed some promise, right?
Oh, yeah, they did. NF is pretty good at separating ions with different charges. So getting monovalent lithium, which has a single positive charge, away from divalent magnesium with its double positive charge, NF can handle that reasonably well.
But there's always a but.
The big but is separating ions with the same charge, like lithium and sodium. Both are monovalent. NF membranes really struggle to tell those apart effectively.
And sodium is a major impurity in these brines, so that's a huge problem. You just pull a lot of sodium through with the lithium.
Exactly, which is why electrically driven systems like electrodialysis or ED started looking more attractive.
How does ED help?
ED uses an electric field to drive ions across membranes. The big pluses are that it's solvent-free, Potentially lower carbon emissions, it's compact, scalable, and crucially, it doesn't depend on the weather.
Ah, okay. So you take the evaporation ponds out of the equation.
You do. Makes it much more reliable for places like, say, Northern Europe or anywhere. You can't rely on constant sun and dry air. It works for brines, even potentially seawater extraction.
But even ED had its own limitations, right? It wasn't a magic bullet with the membranes available then.
Correct. Standard ion exchange membranes, things like Nafion, which are widely used, they have high ionic conductivity, meaning ions move through them easily.
Which sounds good.
It is, but they're just not selective enough for lithium in these complex brines. They let lithium through, sure, but they also let through too much sodium, potassium, etc. It's like having a bouncer who lets almost everyone into the club.
Not very exclusive.
Not at all. So researchers started looking at incorporating inorganic, solid-state electrolytes, materials known as lysicons.
Lysicons?
Yeah, these are ceramic-like materials that are known to be really good conductors of lithium ions specifically. Very selective.
Okay, that sounds promising.
It was, in theory, but the major drawback was their mechanical properties. They are incredibly brittle, like fine china.
Not ideal for an industrial process.
Not at all. So the challenge became, how do you take this fantastic lithium conductivity and selectivity of a brittle ceramic and somehow embed it into a flexible, usable polymer matrix without ruining its performance?
Right, you need the precision of the ceramic, but the toughness of a plastic, sort of.
Exactly. It was a real design paradox.
Yeah.
How do you blend those two seemingly opposing properties?
So, faced with brittle ceramics and non-selective polymers,
Yeah.
how did they finally crack this? What's the core idea behind this LATP-CA membrane we're looking at today?
This is where the cleverness of the materials science comes in. The researchers behind this study developed this membrane by very carefully choosing and combining three key ingredients.
Okay.
First, the star player, LATP. That stands for lithium aluminum titanium phosphate. This is the lithium carrier, the highly selective part.
Why LATP specifically?
Well, it has excellent lithium-ion conductivity. It's known for being very selective for lithium, and it plays relatively well with polymers. Plus, the elements, lithium, aluminum, titanium, phosphorus, are relatively abundant and cost-effective.
Yeah.
Definitely. And importantly, it's chemically stable, works over a good range of electrical conditions, and it's stable in air, makes it robust.
Okay, so LATP is the selective engine. What else?
Second is the matrix holding it all together. Cellulose acetate, or Ca.
Like old camera sill.
Similar base material, yeah, but chosen here because, one, it's biodegradable, a big plus for sustainability,
Good point.
and two, Ca has these things called hydroxyl groups, little chemical hooks, basically. These can actually help improve the ionic conductivity pathways within the membrane and also make it mechanically stable, so it's not just inert filler.
Interesting. It actively helps.
Seems so.
All right.
And the third ingredient was polyethylene glycol, or PEG. This was added to sort of fine-tune things.
What did PEG do?
It acts as an additive to further improve the stability and, importantly, the flexibility of the cellulose acetate matrix. Makes the whole thing less stiff, more resilient.
So you've got the selective LATP, the helpful and biodegradable Ca matrix, and the PEG for flexibility. A nice little team.
A well-thought-out combination, definitely.
And how did they actually make the membrane? Was it complicated?
Actually, the fabrication was pretty standard, a solvent evaporation method, but the key was optimizing the recipe. They found the sweet spot was 50% LATP by weight.
50%. Why was that specific number important?
That concentration allowed the LATP particles to be distributed really uniformly throughout the Ca matrix. It created this dense, integrated structure, and critically, it resulted in a membrane that was surprisingly flexible.
Ah, so they overcame the brittleness problem. That sounds like the aha moment.
It seems like a major step forward, yes. Getting that flexibility while keeping the LATP functional was key. The final membrane was also quite thin, around 60 micrometers.
About the width of a human hair.
Roughly, yeah.
And did the LATP keep its special structure inside the polymer? Was it still able to do its job?
That's crucial, and yes, tests showed the LATP maintained its essential crystalline structure, the specific internal arrangement of atoms, even when embedded in the Ca.
And that structure is what makes it selective for lithium.
Exactly. That ordered structure creates specific pathways that only lithium ions can easily navigate. And importantly, the ion transport happens through these LATP pathways, not just through random holes or pores in the cellulose acetate. That's key for the selectivity.
Okay, structure sounds good, flexibility sounds good. How did it actually perform? Let's get into the numbers.
Right, the electrochemical performance. This is where it gets really interesting. They measured the ionic conductivity, how easily ions move through. For lithium ions, it was remarkably high, 0.677 millisiemens per centimeter at room temperature.
And how does that compare to the unwanted ions?
That's the key comparison. The conductivity for lithium was roughly double the conductivity measured for sodium, magnesium, and calcium ions.
So lithium gets an express lane,
A
essentially.
much faster lane, yes,
Yeah.
while the others face more resistance.
Now, you mentioned temperature earlier. How does that play into it? Usually things get faster when hotter, right?
They do. Ionic conductivity generally increases with temperature for all ions, but here's a fascinating twist. The selectivity of the membrane for lithium over magnesium and calcium actually decreased at higher temperatures.
Really, so hotter isn't necessarily better for separation.
Apparently not in this case. It suggests that running the process at moderate temperatures might be optimal for getting the best lithium purity. It's a subtle but important finding.
Why would lithium move so much more easily, though? What's the mechanism?
To understand that, we look at something called activation energy, EA. You can think of it as the energy barrier an ion has to overcome to jump through the membrane material.
Lower barrier means easier passage.
Exactly. And this LATP-PCA membrane showed a significantly lower activation energy for lithium, just 0.15 electron volts.
How does that compare?
It's quite a bit lower than the others. Potassium was 0.18 eV, sodium 0.19, magnesium 0.21, and calcium needed 0.26 eV. So lithium needs much less of an energy push to get through.
Like it has a VIP pass.
Sort of, yeah. And interestingly, the researchers suggest those hydroxyl groups in the cellulose acetate we mentioned earlier might actually be helping here.
The CA matrix again. How?
They think these groups might create additional conductive pathways that coordinate with the cations, essentially helping to ease lithium's passage specifically. It's a synergistic effect between the LATP and the CA.
That's clever design. Okay, so it works well with single ions. What about slightly more complex mixtures? They tested binary solutions, right? Two types of ions together.
They did, and the results were still strong. They saw impressive lithium-ion fluxes rates of movement up to about 64 millimoles per square meter per hour in a lithium-sodium chloride mix.
And the selectivity. Could it still pick out the lithium?
Yes, quite well in these simpler mixes. The selectivity of lithium over magnesium was about 37, over sodium was 12, and over calcium was around 5.5.
Those seem like solid numbers showing it prefers lithium.
They are definitely promising.
Yeah.
But there was one ion that proved a bit trickier, potassium.
Ah, what happened with potassium?
The selectivity for lithium over potassium was much lower, only about 1.0. Basically, it didn't distinguish between them very well in these binary tests.
Why was potassium different?
It seems to be a combination of factors. Lithium and potassium have somewhat similar ionic conductivities on their own, and in these binary tests, potassium seemed to have a competitive effect, hindering lithium's movement a bit.
Okay, so a potential weakness there.
Yeah,
Which really leads to the crucial test, doesn't it?
absolutely.
How does this membrane handle the real deal? The complex, messy soup of an actual Salt Lake brine? Because that's where the rubber meets the road.
Precisely. This is where many promising lab concepts can stumble. So the researchers simulated a real brine, specifically mimicking the composition of Salar do Uyuni in Bolivia, a major lithium resource.
The ultimate challenge. And what did they find?
They found something really critical and maybe a bit counterintuitive. Applying a lower electric current, specifically negative 200 microamperes, was much, much more effective for separating lithium than using a higher current, like negative 1000 microamperes.
Less is more.
Because at higher currents, while lithium transport increases, the transport of the competing ions increases even more. You end up pulling more impurities across with the higher power. It's about finding the right balance for selectivity, not just brute force transport.
Surgical precision, not a sledgehammer.
Exactly. And under that optimal low current, the results were pretty stunning.
How stunning.
Magnesium concentration, for example, was reduced by about 300-fold in the solution that passed through the membrane.
Wow, 300 times less magnesium.
Yeah. And overall, the rejection rates for sodium, potassium, and magnesium were all over 90%. The membrane was very effectively leaving them behind in the original brine.
And the selectivity in the brine. Did the potassium issue resolve itself?
This is where it gets really impressive. The selectivity actually shot up dramatically in the complex brine compared to the simple binary tests. Lithium over magnesium selectivity soared to nearly 470.
470. compared to 37 before.
Yes. And
Huh.
lithium over sodium jumped to almost 45 compared to 12 before. Even potassium rejection was over 90%.
So the complex environment somehow helped the selectivity. That's fascinating.
It suggests some complex interactions at the membrane surface in the real brine mixture might actually favor lithium passage even more under those low current conditions. It's a fantastic result.
Okay, so one pass gets you much purer lithium. But for batteries, you need incredibly high purity, right? How do you get even closer?
That led them to try an innovative two-step process. Very logical, really.
What did they do? Just run it through again?
Essentially, yes.
Mm.
They took the permeate the solution that had already passed through the membrane once under low current and used that as the feed for a second separation step, using the same membrane setup.
Like a double filter.
Exactly. And the results after this second pass were truly remarkable.
Go on.
The main competing ions, sodium, magnesium, and calcium, were almost completely removed. Their concentrations dropped to incredibly low levels, zero point 0.3 parts per million for sodium, 0.2 ppm for magnesium, 0.4 ppm for calcium.
Tiny amounts, practically gone.
Virtually gone. Even potassium, the trickiest one in binary tests, was knocked down to just 15 ppm. Compared to the starting brine, these reductions were between 70-fold and an incredible 20,000-fold.
20,000 times less magnesium, potentially. That's incredible purification. What about the lithium? Did they lose a lot of it?
That's the other crucial part, no. The lithium concentration in the final purified solution was 18.4 ppm, very close to its concentration in the original brine.
So massive impurity removal with minimal lithium loss. That's the dream scenario.
It really is. And the selectivity numbers reflect that. After 2 steps, the selectivity of lithium over sodium reached an astounding 543.
Wow. Almost perfectly selective at that point.
Extremely selective. And the whole 2-step process, it took just 12 hours.
12 hours.
Yeah.
Compared to months or years for solar evaporation.
Exactly. It's a massive advantage in terms of time, land use, and likely energy efficiency, although detailed energy studies would follow. It points towards a genuinely sustainable and efficient pathway.
And one last crucial factor for real-world use. Stability. Can the membrane hold up over time, especially if conditions change?
Good question. They tested that too. They ran it for 40 days under different pH conditions. Acidic, neutral, alkaline, because pH can fluctuate in industrial systems.
Did it degrade?
It held up very well. There was minimal mass loss, only 2% in simulated brine, 4% in alkaline solution, and about 9% in acidic conditions over those 40 days.
That sounds pretty robust.
It suggests good potential for long-term operation in real-world systems. It's not just a fragile lab prototype. It seems quite durable.
So wrapping this up, we've taken a deep dive into what looks like a really significant step forward for lithium extraction.
Absolutely.
This LATP-CA membrane, cleverly combining that selective ceramic with a flexible biodegradable polymer. It seems to offer a genuinely sustainable and incredibly selective way to get lithium from these challenging salt brines.
Yeah, the performance is impressive. It dramatically outperforms traditional methods in, well, almost every way that matters: speed, selectivity, environmental impact.
That two-step, low-current process achieving such high purity in just 12 hours, that feels like a potential game changer.
It really does. It addresses the core bottlenecks of existing methods. It's a fantastic example of nanoscale engineering solving a macro-scale problem.
And the implications are huge, aren't they? For the clean energy sector, meeting that soaring global demand for lithium, this is the kind of innovation we need.
It really is. It could help make the entire battery supply chain more sustainable and potentially more secure.
Which brings us to our final provocative thought for you, the listener. As you go about your day, think about this. How might innovations like this LATP-CA membrane start to shift the economics, maybe even the geopolitics of critical resources like lithium?
Interesting point. Could it make new, previously uneconomic sources viable?
Possibly. And looking further ahead, what new possibilities might open up if we have more abundant, sustainably sourced lithium? Could it accelerate not just current battery tech, but maybe enable entirely new energy storage solutions or other applications we haven't even thought of yet?